All right, good morning, everyone. Today, we're going to look at the last two circuits for chapter 4, the derivation of the equations, which should go by fast because they are similar to the natural response circuits. And then we look at 3 examples, 2 for natural response and 1 for step. And then homework for chapter 4 is due Sunday night. And then Monday morning, we'll have a quiz as usual. The quiz will be based on chapter 3, not on chapter 4. Because, well, for one, we missed the quiz last week because of the holiday. And then, as you will see in examples for this chapter, that the actual solution is rather straightforward. All you have to do is plug and play, kind of plug the values in. Determining the values will call upon your knowledge about chapters 1 and 2. Okay. So chapter 4 is about understanding how you're going to apply the equation, determining the values for the charge and the full discharge, and then simply plugging it into the solution. All right, so let's begin. We stopped, let's see, there it is. Section 4, we stopped right here. Summary slide for natural response analysis procedure. In the next 4 slides, or the step response, meaning the charging response for RL and RC. So here we have an inductor. When time t is equal to 0, the switch closes, meaning it gets connected to the voltage source Vs. Now, whether the source is a voltage source or a current source, it does not matter. We are trying to find the expression for IL of t, the inductor current as a function of time, meaning we need values for the current for the inductor before and after the switch is closed. So 0 minus and 0 plus, because those describe the initial conditions. Because this is a series circuit, the current I remains the same for all 3 components. Okay, that makes our job easier. So similar to the natural response circuit, to find an expression for IL, we apply KVL and you obtain the exact same expression. Except in this case, because there is a source present, the sum of the voltages do not equal to 0. They equal to the source voltage Vs. Okay, so this is VR and VL. In a natural response circuit, VR plus VL equals 0. In this case, it equals the source voltage Vs. It's a first order differential equation, the solution of which is given by I of t is IF plus I0 minus IF e raised to minus t over tau. It's the exact same equation as the natural response, or I should say exact same structure as the natural response equation. Okay, there's an exponent in there, e raised to minus t over tau. The tau value is exactly the same. That does not change. That is the same for charging and discharging. Okay, that does not change. Tau value always remains L over R. L over R. So as I was saying, the KVL expression includes the source voltage. And so when we solve this, we have an extra quantity in there, IF and I0. IF and I0. Again, the structure is very similar to the natural response circuit, and you will see in just a few slides how it is useful. Okay. And again, if students are interested in the derivation, you can stop by my office. I'll point you in the right direction. You can take a look at the solution for the differential equation. There are a few steps involved before we arrive at this final expression. Sorry, what? Oh, previous slide, yes. There you go. All right, any questions before I move on? Okay, so then let's look at the same response for a capacitor. Oh, one final thing, sorry. So I chose current on purpose because we're writing a KVL, but we can determine the current by applying Ohm's law, right? So this is a voltage source. It's a voltage source, right? Vs. But for an inductor, we always write an expression for the current, IL of t. So the final value of the current through that inductor is always given from Ohm's law, V equals IR. And so I equals V over R. Final value is the source voltage Vs divided by R. Okay. And same thing for the capacitor. We want to write an expression for the voltage across that capacitor, but I'm showing a current source Is, time t equal to 0. The current source is connected to the capacitor, starts charging. And I apply KCL. Is is IR and IC. Obtain an expression. Again, this is IR. This is IC, capacitor current C. Again, the sum of the currents do not equal to 0. They equal to Is. We solve that expression and we obtain the exact same expression that we did for the inductor. V of t is Vf plus V0 minus Vf into e raised to minus t over tau. No difference. All right, any questions? Oftentimes in circuits, there is a switching action, and that switching action causes a input voltage or current to be applied in form of a step, and so it's a step response. So, we call it forced or natural. I prefer not to use the word forced. It has like sinister connotations, and so I try to avoid using that. Okay. So we see that they all have the same structure, right? So from there, we can write a general solution or a general expression for all 4 circuits. Okay, it is a general expression for all 4 circuits. X of t is given by xf plus x0 minus xf, where x as a variable can represent both voltage and current. Okay, x is a variable that can represent both voltage and current. And so if it's an inductor, x is current I. If it's capacitor, x is the voltage V. It represents IL and VC. We want to find the equivalent circuit, or we redraw the circuit for time t less than 0. And you will see that in the example. And then you redraw it again for time t greater than 0. Because both circuits would be different. Okay, circuits will not be the same. Then we simply find the values, the initial values and the final values, x0 and xf. Okay, x0 and xf, and that will be determined from the 2 circuit diagrams. Find tau. and then directly plug in the values into the expression. Okay, directly plug in the values of the expression. And that's it. There's only three quantities you need to find: the initial value, the final value, and tau. That's it. And for this class, meaning this specific class, EE201 for non-EE majors, the fixed value, for the final value and the initial value for the natural and forced response, one end will always be fixed. If it's discharging, meaning it's natural response, it's discharging, F, the final value will always be equal to 0. If it's charging, then the final value will always equal the source value. That's it. See, if it's charging, it's going from 0 to some max value, which is the source. And if it's discharging, it's going from a max value all the way down to 0. And so the values would be flipped. If it's discharging, the initial value, actually, let me not use I, it gets confusing. Or let me use initial. Initial value would be the max source value. Max value or the source value. And here the initial value would be 0. So it gets flipped. In real life, that's not the case, right? It could be, for instance, an example that I use for EE major classes is you might start at 0, you would reach full charge. Then it starts discharging, but before it can go all the way to 0, it starts charging again. And so in that case, the initial value for that charging is not 0. But for this class, for EE201, for non-EE majors, I always take it as 0 and max. Okay. So for discharge and for charge, it's the same thing. The only thing is it's going to be flipped. That's all. All right. Do the steps make sense? Does the equation make sense? And I'll show you right now why it would work for natural response. For natural response, the final value is 0. So if you plug in 0 in this expression, you would obtain x of t is x0 times e raised to minus t over tau. For natural response, xf is equal to 0. And so you obtain the exact same expression that you did when we saw those first two circuits on Wednesday. Okay. Does that make sense to everyone? Right. Okay. Any questions before I move on to the examples? Any questions at all? Okay. All right. Let's move on to example. Oh, sorry. 2 more slides before I move on to example 1. So universal time constant chart and then universal time constant values. Okay. If you take that expression and you plug in the values for t as equal to the time constant products, 1 tau, 2 tau, 3 tau, and so on and so forth, you would get this kind of curve. This is for charging, and this is for discharging. No matter the value of the capacitor, no matter the value of the inductor, no matter the values of the source, the exponent is common to all equations. And so it will always follow this kind of path. And you would have the values pretty much constant as a function of tau, as a product of tau. The values, when equated to 1 tau, 2 tau, 3 tau, till 5 tau, are given in this table. And I will just explain the first value. First value is e raised to minus t over tau, where t is 1 tau. So then it becomes e raised to minus 1, which is equal to 0.3679. 0.3679. Okay, 36.79%. What it means is, if the component is discharging, if a component is discharging, it loses 63.21% after the first time constant. It falls from a max value down to 36.79% of the max value. So it loses more than 50% of its stored energy within the first time constant, from max to less than 50, less than 60 actually, right? It loses 63.21% of its max value. And conversely, the same thing applies for charging. When it's charging, it acquires more than 50% of the max value after one time constant. It reaches 63.21% of the max value. And that's what those equations mean, right? Natural response is V0 into e raised to minus t over tau. So V0, which is the max value discharging, times e raised to minus 1. That's what it means. And then the second and final point is about the final values. See, this is a mathematical expression. It's a function of time. So if you put in a large value of time, whether 1,000 or 1,000,000 or 1,000,000,000 seconds or 1,000,000,000 minutes, you will always obtain a mathematical value for the voltage or the current. But in real life, that's not the case. Right? In real life, we always put an end to it after 5 time constants. That is standard and generally accepted convention that after 5 times tau, it's considered either as fully charged or fully discharged after 5 time constants or 5 times tau, because it has acquired or lost more than 99% of its max value. So we put an end to it after 5 time constants. Make sense? All right. Shall we move into the examples? Okay. Example 1 shows an inductor. And the problem statement is that the switch in the circuit has been closed for a long time. Before it is opened at t equals 0, you're asked to find an expression for the inductor current IL as a function of time when the time values are greater than or equal to 0. Let's analyze the statement. The first thing is a long time. What does it mean? Long time simply indicates that the system is at steady state and the inductor has had sufficient time to reach full charge and is at steady state. So steady state simply means the inductor has acquired all of the energy coming from the source to its max capability, and it is now behaving like a short circuit. That's the first thing. Second thing is the switch is opened at t equals 0. We are asked to find inductor current as a function of time only for the t values greater than or equal to 0, which means we are not concerned with the inductor expression in the past. We are not concerned with what happened prior to time t equals 0. The only thing we are concerned with is what happens after time t equals 0. We, of course, need the value of the current right before the switch is open. So we want a little bit of the past, but we are not analyzing the past. Does that make sense? Right? At some time in the past, of course, the source was first connected to the circuit and the inductor started charging. We are not concerned with any of that because of this phrase right there, a long time. Long time simply indicates the system is at steady state. So let's begin our analysis. For t less than 0, I'm going to redraw my circuit. And I can see that the current source switch was closed. So the current source was connected to the inductor. And because it was connected to the inductor for a very long time, the inductor is behaving like a short circuit. And if it's behaving like a short circuit, my circuit reduces to simply this. That's it. It reduces to this. It's a short circuit, right? And if it's a short circuit in parallel with the source, anything other than the short circuit is effectively removed. Current will always take the easiest pathway to flow through. So R for a short circuit is equal to 0. 0 ohms. If it's 0 ohms, all of the current is flowing through there. Nothing goes through the other resistors. And so my IL at 0 minus is 20 amps. Again, this is still time t less than 0. So IL, the inductor current, right before the switch is opened, is 20 amps. Again, all of this is basically just concepts and your analysis concepts from chapters 1 and 2. Now the switch is flipped open. So for time t greater than or equal to 0, the source and the resistor are disconnected. And the only thing left in the circuit is the inductor along with the 3 resistors. Take note of the current direction. It is already given to us in the problem statement. Okay, the current direction is already given to us. We cannot change that current direction. You have to keep it the same. So now the inductor is the only charged or source of energy in that circuit. Which resistor is the inductor discharging from? Through which resistor is the inductor discharging? All of them, because all 3 of them are connected to the circuit, so it's discharging through all 3 of them. Now, in an EE major class, we ask them to find the voltage across this specific resistor, the current for this specific resistor, which is not something I would do in this class. Okay. So if you have 3 resistors and they're all part of the circuit, what do we do? Reduce them. Reduce them to find Req as seen by the inductor. As seen by the inductor. And so you find Req between those terminals where the component was connected. Okay, Req between the terminals where the inductor was connected. So Req in this case gives me, what does it give me? 40 in parallel with 10 plus the 2 ohm resistor. The Req is 10 ohms. Okay, 10 ohms. We good so far? Okay, so I have Req as 10 ohms. I can find tau, right? I have L, I have Req. My tau is simply L over Req. L is 2. And so this gives me 0.2 seconds. 0.2 seconds. Now, for time t greater than 0, I need to find value for IL. And IL 0 plus, why is this? IL 0 plus is the same as IL 0 minus, which is 20 amps. So my initial conditions are established, and I0 has a value of 20 amps. One more quantity remains, and that is IF, the final value, which in this case is the natural response circuit. Nothing else is stated. Discharging process is not being interrupted. So it discharges all the way to 0. And so IF is 0 amps. Let's take a pause and think about this. Okay. We drew the circuit for time t less than 0. We extracted the information that the current through the inductor is 20 amps because it's at steady state. And if it's at steady state, it behaves like a short circuit. It has reached full charge. Then we redraw the circuit for time t greater than or equal to 0. We see that the source is disconnected. The inductor, the fully charged inductor, is now being discharged through the 3 resistors. And we find Req. Then we find tau. Once we find tau, we establish the initial conditions and find the total current in that inductor right after the switch is flipped, which is 20 amps. And then the final value for the current is 0. All that remains is to plug it into our standard expression, or the general expression, which is given by IL of t is equal to IF plus I0 minus IF into e raised to minus t over tau. Plug in the values, you get 0 plus 20 minus 0 into e raised to minus t over 0.2. Reduce it, and we obtain 20 times e raised to minus 5t minus 5t. And all of this has units A or amps, because the quantity is still current I. It may be a function of time, but it is still a current quantity. So it's amperes. And this equation is valid for all values of t greater than or equal to 0. That's weird. That's better. Let's take a look at that expression. If you plug in t equals 0, what do you get? If time t in this expression is equal to 0, what do we get? E raised to 0, which is 1. 20 times 1, 20 amps, which is the value that we established at the beginning. So this equation is valid for all values of t greater than or equal to 0. If you plug in t is equal to minus 1, it's not going to work, because that equation is no longer valid. All right, questions. As I stated, the solution is not, it's not difficult. It's straightforward. Okay. So all you need are the 3 values: the initial value, the final value, and the time constant tau. And then you simply plug it into the standard form and you write down the solution. The most important part is in the setup and how the expression change. I mean, how the circuit changes for time t less than 0 and time t greater than 0. All right, any questions before I move on to example 2? Any questions at all? Okay, example 2, very similar to the inductor example. We now have a dual position switch. When it's connected to X, the position connected to X for time t less than 0. Actually, let's back up. Let's look at the problem statement. Switch has been in position X for a long time. Anytime you see those words, it indicates the system is at steady state. In this case, the capacitor has had sufficient time to reach full charge, and it's now at steady state. So if I have to draw the diagram, it's minus 10 kilo ohms capacitor is full charge. We are not concerned with the expression before the switch was flipped. Okay, the only thing we are concerned with is that the capacitor was fully charged or is fully charged. So VC 0 minus is 100 volts. Okay, the only thing we care about is inferring and concluding that a capacitor is at steady state, meaning the voltage across that capacitor is 100 volts. All right. Then the switch is flipped, time t greater than or equal to 0. Once it's flipped, we again have a similar circuit. A fully charged capacitor is connected to 3 resistors. The source and the 10 kilo ohm resistor on the left are disconnected, and it's now a natural response circuit. So you identify that this is a natural response. Natural response circuit. And we find Req as seen by the capacitor. So Req as seen by the capacitor gives me, it's actually very similar to the previous problem. 2 resistors in parallel with the one in series. It gives me Req value of 80 kilo ohms. I can find tau as the product of Req and C. And so it's 80,000 times 10 microfarads. Sorry, 0.5 microfarads. So tau is simply 40 milliseconds. 40 milliseconds. Okay. Excuse me. Voltage across a capacitor cannot change instantaneously. So VC at 0 plus is the same as VC at 0 minus, which is the fully charged value of 100 volts. Okay, VC is 0 plus. So my initial conditions imply that V0 equals 100 volts. And because this is natural response problem, VF is 0. Initial voltage V0 is 100, VF is 0. And that's it. my three quantities. I have the values for the three quantities. I can plug in directly into the equation. So Vc of t is Vf plus V0 minus Vf into e raised to minus t over tau. Value for Vc of t is given as 0 plus 100 minus 0 e raised to minus t over 40 milliseconds. And therefore Vc of t is 100 times e raised to minus t or minus 25t. Entire expression has a unit of volts. This expression is valid for all values of time t greater than or equal to 0. All right, 10-second pause. Let me know if you have any questions. Again, the goal is to identify the circuit parameters by redrawing the circuit. You establish the initial conditions, find the initial value, meaning I0 or V0, and find the final values, meaning IF and VF or VF. And then simply plug it into the expression, the general expression, and you'd have your answer. All right, any questions? Any questions at all? No questions? Then who wants to come up here and solve for example 3? It's straightforward, but this is a step response. So time t less than 0, the switch is closed. If the switch is closed, the capacitor and the resistor are not part of the circuit at all because the short circuit is in parallel with the current source. Now understand that in real life, this would never be the case. We would not take a source and short out its terminals. Okay, this is just to illustrate that because the switch has been closed, all of the current is flowing through that short circuit pathway. The capacitor and the resistor are left alone. So the capacitor is fully discharged, meaning the initial conditions are implying that Vc at 0 minus is equal to 0 volts. All of the current is flowing through the switch or the short circuit. Okay, nothing is going through the resistor or the capacitor. Any charge the capacitor had previously is already discharged through that 2 kilo ohm resistor. That's all it is implying. Okay. Then at t equal to 0, the switch is opened. When the switch is opened, the source is now connected to the capacitor. It starts charging. Eventually, it is going to reach full charge. And the value of that full charge can be obtained by applying Ohm's law to the source. Vf would be equal to Is times R. In this case, it would be 10 milliamps times 2 kilo ohms This would be 20 volts. Voltage cannot change instantaneously across a capacitor, so VC of 0 plus is the same as VC at 0 minus, which is 0 volts. My tau is simply RC, which is 2000 times 10 microfarads. And so tau value is 20 milliseconds. And that's it. I have my three quantities. V0 is 0. Is 0 volts, and VF is 20 volts. I can directly write an expression VC of t as VF plus V0 minus VF to e raised to minus t over tau. Plug in the values and you get VF is 20 plus 0 minus 20 into e raised to minus t over 20 milliseconds. VC of t is 20 minus 20 into e raised to minus 50 t. So all has a value of volts, and this expression is valid for all values of t greater than or equal to 0. Let's take a very long pause while you write it down, think over it. Let me know if you have any questions. Yes. So I was going to do a recap right now anyway. So time t less than 0, problem statement says for t greater than 0, we have to derive an expression for the capacitor voltage. Nothing else is given to us. Absolutely nothing is given to us, right? This is one of the reasons I chose this problem. The circuit itself is very simple, but everything else has to be derived just by looking at the circuit diagram. So switch arrow is shown as being open at time t equal to 0. So that implies that prior to time t equal to 0, meaning when t was less than 0, the switch was closed. If it's closed, there's nothing in this path. R is equal to 0. If R is equal to 0, current is infinite. All of the current will always take the path of least resistance. So all of the current is flowing through that pathway. Now, again, in real life, this would never be the case. We would not short out the terminals of a power supply. It would simply explode, right? So we do not do that. But the purpose to use this in this particular example is to show that the capacitor is disconnected from the rest of the circuit. So the capacitor, whatever charge the capacitor had in the past, has been discharged through that resistor R. That's the only purpose to show this short circuit. Meaning prior to it being switched, the capacitor discharged through that 2 kilo ohm resistor. That's the only purpose. Just to infer, just for us to conclude that the capacitor is completely discharged and VC at 0 minus is equal to 0 volts. It's only to establish the initial conditions. So V0 is 0 volts, which is right here. And then once the switch is opened, it starts charging. The final value is given from Ohm's law. VF would be IS times R, so 10 milliamps times 2 kilo ohms gives us 20 volts. So we have V0, we have Vf. The only thing we are missing is the time constant tau. We can find it simply by the product of R and C. Once we have all three, we simply plug it into the expression for the general solution, and we obtain this. And that's it. So now it doesn't matter if you as engineers, if you come across this kind of problem, you should be able to break it up into different pieces depending on what the problem statement gives you. The problem statement says time t equal to 0, the switch is flipped to position 1. 5 milliseconds later, it goes to position 2, and then position 3 and 4 and 5, so on and so forth. For every position the circuit changes, you would simply redraw the circuit for every step, find the initial and final values for every single step, and you can directly write down the solution for that particular time period. And that would be it. That's all you would do. All right, any other questions? Okay, so that is the end of chapter 4. Again, the homework is due on Sunday night. We introduced the topic on Wednesday. Most of the concepts were covered on Wednesday, and most of the questions in this homework are conceptual questions, short answer questions based on the theory. There are some problems in there, so now you should be able to handle the problems also, right? If you have any questions, I'll be in my office. I'll be in 131 and then 130. There's a demonstration of new equipment taking place. So I'll be right next door. So if you do come by my office, I'll be right next door. I'll also be available over Zoom via email over the weekend. So if you have any questions, reach out to me. All right. We'll end class here today, and I will bid you all a good weekend. And I will see you all on Monday.